Yes, hey, welcome back. And now let us solve a very wacky problem called lead to DDL. And believe me, when I saw this problem, I lost my mind. But when I came up with a solution, it was not that bad also. And but the question is very wacky indeed. So what is the question? The question is that you are given a binary tree, and you are to extract all the leaf nodes to form a double linked list, starting from the leftmost node, and you are supposed to modify the binary tree. And yeah, and you are supposed to modify the binary tree in such a way that all the left nodes of the binary tree will actually be the previous pointer of the doubly linked list, and all the right nodes of the binary tree will be the next node of the doubly linked list. And yeah, so that is pretty wacky. So if you consider this tree 1, 2, 3, 4, 5, 6, 7, so 1, 2, 3 will be extracted out, and 4, 5, 6, 7 will be extracted out, and you'll form a double linked list with 4, 5, 6, 7, and you'll return one like, and 1, 2, 3, and 4, 5, 6, 7 will be printed out. And yeah, that's why I told this is very, very wacky. And first, I try to come up with any form of solution. And first, what I thought was that I could do a vertical L or a traversal to get all the nodes from left to right. And then what I would do is that I would directly disconnect them. And after doing that, like I could directly connect them in the form of double English. But the issue with that is that it won't work. And then I remember doing another very similar problem, which was flattening a linked list to a binary tree or something, where what happened was that in order to get the leaf nodes in the form of 4, 5, 6, 7, the you can get it in one way, and that is to do an actual in-order traversal. And when you do an in-order traversal, first you will check the left node, and then check the root node, and then you check the right node. In other words, you'll check for 2, first you'll check for 4, and then 2, and then 5. So in other words, 4, 5, 6, 7 will all be checked in order. So what my train of thought was that first I would do a in-order traversal to get all the leaf nodes, and then I would do a level order traversal to disconnect all the leaf nodes from their parent node. And then what I can do is that I can store that leaf node, disconnected leaf nodes somewhere in an array or something, and then at the end I could just connect them. And thankfully that time approach worked out. So again I'll tell you what is to be done. So first what we'll do is that we'll do a level order traversal to, yeah. So let's just take this tree itself. So you have 1, 2, 3, 4, 5. Pardon my drawing. I'm not good in drawing. And yeah, and then you will just have this connection. So what you will do is that first we'll do a level order traversal. So we'll get the values of 5, 6, 7, and 4, 5, 6, 7, and you store it in an array. So 5, 6, 7, and 4. Yeah, you will have this in an array. And then what you will do is that you will do an actual level order traversal. So you will get 1, and then you will get the value of 2, and you will see that 2 dot left is the leaf node. So as soon as you see that some dot left is the leaf node, what you will do? You will just erase that link. And then you will see that 2 dot right is the leaf node. So what you will do? You will erase that link. And then what you will do? Then you will check for 3. And as soon as you check for 3, you will see that 3 dot left is the leaf node. So you will erase that link. And 3 dot right is the root node. So you will erase that link. So what will happen is that now 4 has no left or right node. So 4 dot left will be null, 4 dot right will be null, 5 dot left will be null, 5 dot right will be null, 5, 6 dot left and 7 dot left and right will be null. So what you'll do? You will take 4 dot right and connect it to 5. You will take 5 dot left and connect it to 4. You will take 5 dot right and connect it to 6. You will take 6 dot left and connect it to 5. You will take 6 dot right and connect it to 7. You will take 7 dot left and connect it to 6. And then what you'll have that not only is this tree disconnected, uh, yeah. So what will happen is that not only is this tree disconnected from here, but also you will have your doubly linked list. So yeah, so that is the approach which we will follow. So what we will do? First of all, we will have a very important helper function called eSleep node, eSleep, which will take the current node and tell if it is leaf or not. So we will take self and node. And what we will do? If node dot left is not node dot left or not node dot right. So what we will do? We will return ret. You will return true, telling that it is a leaf node. Else you will return false. So we do. So what you will do? First, you will do a as if you remember what I told, you will do a in order traversal to get all the nodes from left to right, like all the leaf nodes. So what you do, you'll have a stack, and then you'll have a current pointer pointing to root because you don't want to actually lose the reference of the root. You want to keep the reference of the root. and while cur exists and the stack or the stack exists, cur is equal to cur dot left, and before going left, while cur exists again, and stack dot append the value of cur, and cur is stack dot pop. This is classic level order traversal. So I mean in order traversal. And if cur dot self dot is leaf, the value of cur. So what you will do? You will have an array for list. So what you will do? For now, I'll append cur dot data itself so that we can see if we actually have our leaf nodes only. And cur is cur dot right. And let me return a node with value 0, and let us just print out the value of this, and let's have some dummy print statements to distinguish our print statement from the driver code. Yeah, and as you see, we have 4, 5, 6, 7, which is the actual leaf nodes. But still, the leaf nodes are connected to your what you call parent node. So what you have to do? Now you have to do a level order traversal to disconnect those leaves. So what you will do from you don't want default dictionary. You want DQ, and then you have the DQ with the value of root. Again, you'll have a curve pointing to the root, and you'll have the value of curve. And while Q exists for something when range length of Q, you will do node is equal to TOPLEFT, yeah, and you pop out the left node. I mean, you pop out the left most value from the queue, and if node dot left exists, and if node dot right exists, yeah. So now you have to do another check. If the node dot left is a leaf node, self dot, yeah, if it is a leaf node, you have to do something, and that is to disconnect the current node from the node dot left. So node dot left will actually be set to none. Only or else what you will do is append the node dot left, and again you will do the same thing over here. If the node dot right is a leaf node, so you'll take the node dot right and disconnect it, or else what you will do, you will append the current node to the right, like you'll append the right node. So again, let's do a dummy level of traversal to just check if our route has been like if our modifications are correct. So yeah, and while q exists for in range length of q, node is actually q dot q e dot, and let us just print node dot data, and we'll have ending delimiter as this, and if node dot left exists, then yes, and if node dot right exists, then node dot right. Yeah. And after doing everything, let's just have another print statement so that we will move to the next line. And let's see if our modifications are done properly. And as you see, 1 and 2, 3 is printed. In other words, our disconnections have been done properly. So the connections of 2 to 4, 2 to 5, 3 to 6, 3 to 7 have been removed successfully. So let's just remove this part. So now what you have to do for I in range. So what we'll do, we will not append the data itself. We'll just append the node range length of what is that list. So you will take the current node, which is nothing but AR at the position I, And let's go till the last index because there's no need for us to do anything with the last index. Node 7 will not have a next node, so we will not do anything with that. So the current node is added at the position I, and the next node is actually added at position I plus 1. And what you'll do, cur node dot right will actually be equal to the next node, and next node dot left will actually be equal to the current node. And actually, the reference to our head also is contained in our array itself. So yeah, so the reference to our array is actually contained in leaves at the position 0. This is actually the reference to the double linked list, and it is somewhere I've written ARR, and it is leaves, leaves. Yeah, and as you see, it is running, and let's just submit it and check it out once. Okay. Mm, why is it failing? Let's just do one. So fail. Let us just check it out, and very interesting. That means it is telling that 3, 2, 4. So the disconnections have not been done properly, I think. I don't think we need to maintain the reference to our current node. So let's just execute this test case again. Mm, so if we have the current node, and if node dot left exists, the node dot left is the leaf node, node left is equal to null, or else q dot up and node dot left, and if right node is null, 1, 4, 3. That should never happen. Why that happen? That means even the tree is not getting merged properly. Let's just do control Z and let's copy this part and let's do control Y again and keep up. Yeah, and let's just print out this one now. Let's just see what is the value of our current tree then. This is with the value of root. So what might be the issue? Mm, okay, okay, and I see that the check from the leaf node is done improperly. So it's not node dot left and the not node dot right. Yeah, this was one of the issues. So now let's just run it. And now, yeah, let us remove the print statement because it's not part not required now. And then now it's working. Let's just submit it. A very small issue was there over here. And yeah, now it's running. That's what you want to see. And yeah, as I said, it works. And this was the small issue over there rather than writing with node dot left and node dot right. If I had written node dot left or node dot right, which is obviously incorrect. So you want to check for both the left and right side. You just don't want to tell only if one of the left child or right child exists is the leaf node. And yeah, that's all for it. And thank you for watching and goodbye.